Good day, everyone. I'm Professor Denzel Albertudes, and our topic for today is all about microscopy. Before we indulge to our lesson, let us first define what is microscopy. Microscopy is a technical field of using microscopes to view objects and areas of objects that cannot be seen with the naked eye. It provides us vision of micro objects, turning it into a macro scale, and is a great milestone of molecular biology. There are three well-known branches of microscopy: the optical microscopy, the electron microscopy, and the scanning probe microscopy. We also have the emerging field of X-ray microscopy. First is the optical microscopy. Optical microscopy utilizes a visible light and a system of lenses to generate magnified images of small objects. For the second well-known field of microscopy, we have the electron microscopy, which uses a beam of accelerated electrons as a source of illumination. Last but not the least, we have the scanning probe microscopy. It is a branch of microscopy that forms images of surfaces using a physical probe that scans the specimen. Let us now move on to our discussion of the compound microscope. Anyone here has an idea of a compound microscope? Well, a compound microscope is a microscope that uses multiple lenses to enlarge the image of a sample. A compound microscope is also an example of optical microscopy since it utilizes light to view objects. The compound microscope was well known when Anton van Leeuwenhoek used it to view the pond and discovered that it is made up of microorganisms, red blood cells, and other tiny organisms. Before we indulge to parts of a compound microscope and its functions, let us go back in time and have a peek of the microscope's evolution. In 14th century, spectacles first made in Italy. Italy was the first country to theorize a technology that zooms a tiny particle into a macro scale. In 1590, two Dutch spectacle makers, the father and son team, Hans and Zacharias Janssen, created the very first microscope. To be specific, a microscope utilizing light, which is now called a compound microscope. However, compared to today's compound microscope, their invention was a lot primitive. In 1667, Robert Hooke's famous Micrographia is published, which outlines Hooke's various studies using the microscope. Robert Hooke was the first to discover the cell. In 1675, Anton van Leeuwenhoek used a microscope with one lens to observe insects and other specimens. Leeuwenhoek was the first to observe bacteria. In 18th century, as technology improved, microscopy became more popular among scientists. Part of this was due to the discovery that combining two types of glass reduced the chromatic effect. In the year 1830, Joseph Jackson Lister discovered that using weak lenses together at various distances provided clear magnification. After 48 years, Ernst Abbe postulated a mathematical theory linking resolution to light wavelength. In 1900s, specifically in 1903, Richard Sigmund invents the ultramicroscope, which allows for observation of specimens below the wavelength of light. In the year 1932, transparent biological materials are studied for the first time using Fritz Zernike's invention of the phase contrast microscope. Just 6 years after the invention of the phase contrast microscope comes the electron microscope. It was developed by Ernst Röske, who realized that using electrons in microscopy enhanced resolution. In the year 1981, a 3D specimen image is possible with the invention of the scanning tunneling microscope by Gerd Binnig and Heinrich Rohrer. Year 2000 and up to now, emerging microscopes are invented. Scientists are able to produce efficient and advanced microscope capable of zooming hundreds of millions of times microscope of the primitive era could do. Hence, we are able to achieve new discoveries in the field of molecular biology. You just have learned about the timeline of microscopy. Let us now move on to the parts of a compound microscope and its functions. A high-power or compound microscope achieves higher level of magnification than a stereo or low-power microscope. It is used to view smaller specimens such as cell structures which cannot be seen at lower levels of magnification. Essentially, a compound microscope consists of structural and optical components. However, within these basic systems, there are some essential components that every microscopist should know and understand. We have here a figure of a compound microscope. As you can see, these are the parts. There are the optical components and the structural components. Wait. There are three basic parts of structural components: the head, the arm, and the base. The head houses the optical parts in the upper part of the microscope. Meanwhile, the base supports the microscope and houses the illuminator. Lastly, the arm connects to the base and supports the microscope head. It is also used to carry the microscope. You should take note that when carrying a compound microscope, always take care to lift it by both the arm and base simultaneously. For the optical components, the two major optical systems in a compound microscope are known as eyepiece lenses and objective lenses. For the eyepiece or ocular, is what you look through at the top of the microscope. Typically, standard eyepieces have a magnifying power of 10 times. Optional eyepieces of varying powers are available, typically from 5 times to 30 times. Eyepiece tube holds the eyepieces in place above the objective lens. Binocular microscope heads typically incorporate a diopter adjustment ring that allows for the possible inconsistencies of our eyesight in one or both eyes. The monocular single-eye usage microscope does not need a diopter. Binocular microscope also swivel interpupillary adjustment to allow for different distances between the eyes of different individuals. For the objective lenses, these are the primary optical lenses in a microscope, which range from 4 times to 100 times and typically include 3, 4, or 5 on lens, most of the microscopes. Objectives can be forward or rear facing. Nose piece houses the objectives. The objectives are exposed and are mounted on a rotating turret so that different objectives can be conveniently selected. Standard objectives include 4 times, 10 times, 40 times, and 100 times, although different power objectives are available. For the coarse and fine focus, these are knobs that are used to focus the microscope. Increasingly, they are coaxial knobs, that is to say they are built on the same axis with the fine focus knob on the outside. Coaxial focus knobs are more convenient since the viewer does not have to grope for a different knob. Stage is where the specimen to be viewed is placed. A mechanical stage is used when working at higher magnifications where delicate movements of the specimen's light are required. For the stage clips, these are used when there is no mechanical stage. The viewer is required to move the slide manually to view different sections of the specimen. The aperture is the hole in the stage through which the base transmits light until it reaches the stage. Illuminator is the light source for a microscope, typically located in the base of the microscope. Most light microscopes use low voltage halogen bulbs with continuous variable lighting control located within the base. The condenser is used to collect and focus the light from the illuminator onto the specimen. It is located under the stage, often in conjunction with an iris diaphragm. The iris diaphragm controls the amount of light reaching the specimen. It is located above the condenser and below the stage. Most high-quality microscopes include an AB condenser with an iris diaphragm. Combined together, they control both the focus and quantity of light applied to the specimen. For the condenser focus knob, it moves the condenser up or down to control the lighting focus on the specimen.
A few moments later.
Things to remember when using a compound microscope. Understanding your microscope. First, familiarize yourself with the microscope. Examine all the parts and learn their function and their names. Check if the parts are complete. The first step is to place your microscope on a clean, level surface near an electrical outlet. Always carry your microscope with 2 hands. Hold the arm with 1 hand. Support the base with your other hand. The second step is to turn on the microscope. This will require plugging it into an appropriate outlet. The switch is usually located in the microscope's base. The electricity illuminates the components in a compound microscope. Make sure your power source is appropriate for your microscope. Commonly, compound microscopes require a 120-volt power source. The third step is to inspect the head and arm. The head holds the optical elements, which include the eyepiece and eyepiece tube, the nose piece, and the objective lenses. It is also known as the body of the microscope. The arm connects the head to the base. There are no lenses on the microscope's arm. The steps are: the eyepiece or ocular is what you look through to see what the object beneath the microscope. The eyepiece tube holds the eyepieces in place. The nose piece holds the objective lenses. The objective lenses are the main lenses of the compound microscope. There can be at least 3, 4, or 5 lenses in a compound microscope, depending on its level of complexity. The arm provides support for the microscope's head. Ito na. The fourth step Examine the base. The base holds up the microscope and provides the stage to place samples onto. The base also contains the focusing knobs, both fine and coarse. Steps are: the focusing knobs may be either separate or coaxial, meaning the coarse focusing knob is on the same axis as the fine focusing knob. The stage is where you place the slide holding the specimen. You can use a mechanical stage when working with higher magnifications. Make sure to use stage clips when you adjust stages manually. In the fifth step, learn about light sources. The compound microscope provides its own light sources for optimal viewing. These light sources are in the base of the microscope. Light enters the stage through the aperture, which allows the light to reach the slide. The illuminator provides light for the microscope. Typically, the illuminator uses low-watt halogen bulbs. Lighting is continuous and variable. A condenser collects and focuses the light from the illuminator. It's located beneath the stage, often together with the iris diaphragm. The condenser focus knob moves the condenser up and down to adjust the light. The iris diaphragm is located below the stage, working together with the condenser. The iris diaphragm controls the focus and quality of light provided to the specimen. Next is focusing the microscope. In the sixth step, you should prepare your slide. Always prepare slides with a cover slip or cover glass to protect the specimen you're viewing with the microscope. This will also protect the lens of your microscope from anything that might press against it. Position your sample between two pieces of glass to make a slide. Place the slide in the center of the stage over the glass hole. Move the two stage clips over the sides of the slide to secure it into place. In the seventh step, make sure that the iris diaphragm is open. This is usually just under the stage. You want to have the best amount of light to reach the slide and the lenses. Don't use the iris diaphragm to control the light. Use it to optimize the level of contrast and resolution for clearer viewing. Use the lowest magnification level needed. Moving on to the eighth step, arrange the revolving nosepiece and knobs. Start with the lowest level of magnification. This will allow you to select the part of the specimen that offers the most interest. Once you've located this, you may increase the magnification to better view this part. Turn the nosepiece turret until the shortest lens 4 times above your sample. It should click and feel rigid when it is in place. The shortest objective lens is the least powerful, the lowest level of magnification. It is the easiest level to begin when magnifying an object. In the ninth step, focus the microscope. Looking through the eyepiece, arrange the illuminator and the diaphragm to reach the most comfortable level of light. Move the specimen slide so that the image is in the center of your view. Arrange the illuminator until you've arrived at a comfortable level of light. The brighter the illuminator shines, the better you will be able to use your specimen. Twist the coarse focus knob the opposite way as you had before, so the stage moves away from the lens. Do this slowly until the sample begins to focus. In the 10th step, magnify the image. Use the coarse focus knob to get the specimen in view, and the fine focus knob to bring the adjusted slide into focus. You may need to reposition your slide as you magnify. When using a compound microscope, the correct viewing technique is to keep both eyes open. Look through the eyepiece with one eye and look outside the microscope with the other eye. When you use the 10 times lens to magnify the image, it may help to lower the amount of light for better clarity. Readjust your illuminator and iris diaphragm as needed. Switch lenses by rotating the nosepiece turret to a longer lens. Perform necessary focusing adaptations. For the last step, put the microscope away. Dust can cause great damage to a compound microscope. It can scratch delicate lenses, clog adjustments, and clutter the images visible through your eyepiece. Always turn off the power when you're finished using your microscope. Lower the stage. Remove your specimen and cover the equipment with the dust repellent cover. Avoid touching any lens or glass with your fingers. Always carry the microscope carefully with both hands. And that would be all for my lesson. I hope you enjoyed watching my video. This is Professor Denzel Verdudes signing off.